Looking at the graph of our function f of x below, we can quickly identify that we have two x-intercepts, the first occurring at -4, 0, and the second occurring at 2, 0. Since we also have our function expressed as an equation, we can look at how we would quickly identify those two intercepts by setting our function equal to 0 and then solving for x. Since our function is already in factored form, we know we can just look at solving each of those factors individually, set equal to 0, which in this case would give us x is equal to 2 and x is equal to -4. That process for finding our x-intercepts then also identifies zeros of our function, since for any value a, if f of a is equal to 0, then that value for a is called a zero of that function. Or in this case, a zero of f of x. So what we've found, essentially, is that f of 2 would be equal to 0, and f of -4 would be equal to 0. So those two values represent our x-intercepts, and also two zeros for this function. Next, we want to consider the behavior of our function at each of these x-intercepts. We can see at our intercept of -4 that what we have is our function decreasing, hitting the x-axis, and then turning back away, changing directions to be increasing. At our intercept of 2, we see that our function is decreasing, crosses over the x-axis, and continues decreasing. So we have two different types of behavior there, determined by what we refer to as the multiplicities, or just the multiplicity of each of our zeros. In this case, our factors actually consisted of x minus 2 to the first power, which gives x equals 2, a multiplicity of 1. And what we actually had is the factor x plus 4, that quantity squared, giving this value a multiplicity of 2. And what we'll see is that pattern continued for any polynomial function. Whenever we have an even multiplicity for our zero, what we'll see is a case where our graph touches the x-axis, and anytime our zero has an odd multiplicity, our graph will cross over the x-axis. We can use intercepts then, or zeros, along with their multiplicities to understand the behavior of a polynomial function around those intercepts. The next thing that we can look at would be identifying the end behavior of our function. We'll start with looking at what happens as x approaches -infinity. So as our x values become very, very small, what's happening is that our function value is getting larger and larger and larger. So it's approaching positive infinity. As our x values become increasingly large, so as they approach positive infinity, our function value is approaching negative infinity. We can see that pretty clearly, hopefully, since we have our function graphed, but we can also identify that behavior by investigating the function itself. In this case, what we need to understand is the degree of our polynomial, so we can identify the power function that corresponds to it for very large values of x, or very small values of x. In order to identify the degree, we would need to look at expanding out this entire polynomial, but that can be a little time consuming, so we're going to shortcut that process a little bit by just looking at whatever constant factor we have out front, and then just looking at the x terms of our remaining factors. So I'm shortening up that expression to again only consider that constant factor of -4, and then just looking at each of my x terms in the remaining factors and any associated exponents. meaning that my function f of x is approaching, in this case, negative 4x cubed. Essentially what we're doing here is looking at just multiplying all of the leading terms together. So what we end up with is the leading term for that polynomial if we were to expand the entire function. Since we know that our function for very extreme values of x is mimicking the behavior of x cubed, we know that our graph is approaching the opposite values in each direction. And since we have a negative coefficient in front, we know that that's a reflection, which means our function for very large values of x is going to be mimicking this behavior, which is what we see in our graph to the left. Obviously, we have some slightly different behavior in the middle, but as far as the extremes go, we get that behavior of approaching positive infinity for very large negative values and approaching negative infinity for very large positive values. The last thing we can look at is the number of turning points on our graph. In this case, our function has exactly 2 turning points, where a turning point is simply defined as a place where our function changes direction from increasing to decreasing or decreasing to increasing. Essentially, what we have at these turning points are local extrema, so a local maximum or a local minimum, or potentially an absolute maximum or minimum. In this case, we have 2 turning points, which is the maximum number of turning points that this particular function could have, because we already know, or what we've established just before, is that this polynomial is a function of degree 3. And the maximum number of turning points that a function can have is equal to n minus 1, where n is equal to the degree of that polynomial. So just looking at this function, once we identify that it's a 3rd degree, we know that this function could have at most 2 turning points. In this case, it has exactly 2, but 2 would be the maximum number.